basically, what I want to first talk about is what is pumping. So, what is pumps and pumping, right? So, basically, what is a pump? A pump is a device for raising or moving water or any other fluid. So, it is a device for raising water or moving basically the water. I mean, of course, it doesn't need to be water. It can be basically any fluid. And by fluid, we mean it could be gas, it could be water, it could be sludge, could be anything, right? So basically, it is primarily for moving fluids. So when you're moving the fluid, there is a what happens is that you will need to overcome the resistance because of the density of that fluid that you are moving. You'll also have to fight the gravitational force. Uh, then also what you'd have to do is you would have to overcome the forces associated with the friction of that fluid in the piping that you're conveying the fluids through, correct? So basically, this particular resistance that we are talking about is basically going to be dependent on other elements, which will include how much of fluid you're moving, like what is the quantity in terms of, say, if you're talking water, it would be in GPM, and also it would be a function of the height of the water that the fluid is being pumped to, which we'll talk about in terms of head, etc. Okay, so let's talk about first things like what is force, pressure, and head. Okay, so basically, force is nothing but in the English system, the force and weight are essentially in the same are used basically in the same way. So what in the SI system, which is the other in the metric system, basically force and weight are different quantities and they are kind of measured differently. But the way things are defined in the English system, the force and weight essentially are measured in the same unit. So when we are talking about, say, in the context of water, so say I have 1 cubic foot of water in this particular cube. So everything is 1 cubic uh, uh, 1 feet in dimension. What happens? What will happen is that the force that is acting on the surface, because this cube is resting on the surface, so the amount of force that is going to be resting on that is going to equal to 60 is going to equal to 60 oops is going to equal to 62.4 pounds. And how do you get that? Water weighs 8.34 pounds per gallon, right? That's something that we typically use. And then you have 7.48 gallons per cubic foot. So that's how, when you multiply this, you get 62.4 pounds per of the weight of water per cubic foot. Agree? So if I hypothetically, if I have two such cubes stacked on top of each other, right? So what is going to happen is that the force that is going to act at the bottom of this is going to be, this height of water is going to be 2 feet, correct? 1 foot each. Therefore, the force that is going to be acting at the bottom is going to be 62. This way, 62.4. This way, 62.4. So therefore, the force acting here is going to be 124.8 pounds. So coming back here, this 62.4 pounds is felt by the surface over an area of 12 inches by 12 inches because it's 1 foot. So this 62.4 pounds is felt over an area of, or is distributed over an area of 12 inches by 12 inch. So this is 12-inch square. So basically it is 62.4 pounds per 144 inch square. Somebody was asking something? Let me see if somebody's in the waiting room or something. Give me 1 second.
Yeah.
And I just did the permissions too, so I didn't realize that it was asking me. Okay. So basically what this means is that per foot of water, you have, this works out to 0.43 pounds per inch square. So this is the same as 0.43 psi. So psi is pound per inch square. So 1 foot of water is equivalent to 0.43 psi, correct? And conversely, basically 1 psi is equal to 1 over 0.43, right? So this is going to equal to feet. So this is going to equal to 2.31 feet. Does that make sense?
Yes.
So this is the concept of force, and the basis for 1 foot is 0.43 psi, or 1 psi is 2.31 foot. Now let's talk in the concept of head. Okay, so what is head? Head is the pressure. So when we talk about head is nothing but the pressure that is exerted by a certain height of a column of water, right? So basically pressure exerted by the height of water. So if I have a tank, and basically it is filled with water, this water is going to exert a certain force, and that force is going to be dependent on how much height of water that is above a certain point. So whether we are talking at about a certain point here, or one thing, maybe I suggest that you mute yourself because the background noise kind of comes through. So it kind of distracts me. So depending on where you're looking at, that much amount of pressure is going to be exerted depending on the height of the fluid. So if I have, so conversely, what we can say is that if I have, say, a water flowing through a pipe, then conversely, what I can say is that a pressure, say there is water that is flowing through this under a certain pressure. This amount of pressure, this pressure is going to exert a head on the water. What that means is, say hypothetically, if I was to put in just a column here, an open tube here, this pressure is going to be able to support a certain height of the water. And this is basically that head that we are talking about. So this is basically the relationship between head and pressure. Does that make sense? So if I have a tube, on top of this pipe, the height of the water that is going to be in that tube is going to be a function of how much of pressure is in the pipe. Okay. So when we are talking about head and pressure, basically one thing we need to make sure that we understand is that irrespective of the shape of the tank, so suppose if I have this conical tank, or like I have a typical water storage tank, or an inverse, or I just have a column of water. And so basically, if this is all of, oops. So if this is all on the same level, or the amount of water is basically the same, irrespective of the shape of the vessel, basically the pressure at the bottom is going to be pretty much the same. It is going to be the same because it's just a function of the height of the water, and it has got nothing to do with the shape of the water. I know this is pretty common sense, but just making sure that we all understand. So suppose if I have a certain tank again, and if I have this tank is filled with water up to this particular height, then if I say this is 10 feet water height at this particular point, so the pressure, if I put a pressure gauge here, this pressure gauge is going to measure 2.31 times 10, which is 23.1 psi. And at the bottom of the tank, assume this is, say, another 10 feet, right? So this is going to be, because this total height is now 20 feet, so the pressure here is going to be 2.31 times 20, which is 46.2 psi. Okay. So having said that, basically, let's just talk about one more thing, which is related to head loss. What is head loss? So when a fluid or water is flowing through a pipe or a piping system, basically what will happen is that some of that energy that is associated with that liquid or water that is flowing through it is going to be lost because of friction. And when we talk about friction, what happens is that as the water is moving through the pipe, what will happen is that there is what is called a friction force that is exerted by the surface of the pipe on the water that is flowing through it. And this friction is normally a function of how rough the pipe is. Means when we say rough, means if the pipe is smooth like a PVC pipe, then there is less friction involved. But if it has a lot of deposition, etc., then basically, yeah, exactly, C value. So C value is essentially a measure of the smoothness of the pipe. So C value is the measure of the smoothness of pipe. And I think a PVC pipe has probably one of the smoother pipes, so it'll be about, say, about a C value of about 140. And then if you have a pipe that is relatively rough, the C value is going to basically be lower, could be even 70 or something in that range. So anyway, so it all depends on the roughness. It depends on the length of the pipe. So of course, so that means if I'm pumping my fluids or water over a longer distance, I'm going to have more friction losses or more head losses. So head loss is basically just make sure it's the loss of energy. That means you will need to provide that much energy, additional energy, to overcome the friction forces. So we talked about roughness, we talked about the length, and then it is a function of the pipe diameter. Why? Because if I have a smaller diameter, actually I can put these two together, the velocity, because they're kind of go hand in hand. Basically, if I have a larger amount of flow going through a certain pipe, that means it will have a higher friction. So the smaller the diameter, then the friction factor is going to be greater, right? For the same flow. So for the same flow, if I have a smaller pipe, that means my velocity is going to be higher. And of course, my diameter is smaller. Therefore, the friction factor is going to be higher, or the head loss is going to be higher. And then finally, the element that affects friction is basically the fittings or the components, of the pipe. So if you have bends and valves and things like that, so when the water changes direction, either say it's going up the hill or it makes a turn, these fittings will cause additional head losses. So basically, fittings could be valves, bends, etc.